Hey, you guys, just thought I'd do a quick video for you for chapter 2 over the PowerPoint slides. My goal is just to go through this quickly and see, kind of give you the high points of this and kind of why we're thinking about this type of thing and what you should kind of focus on. So this is the same PowerPoint that we went over in class. So chapter 2 is about atoms, molecules, and ions. Atoms, molecules, and ions is what chapter 2 is about. So we talked a little bit about Dalton's atomic theory, and the idea was that matter was made of teeny tiny atoms that were no longer divisible at a certain point. So Dalton's atomic theory said that elements were composed of these tiny little things called atoms, and that all atoms of a given size or given element they have the same size, mass, and chemical properties, and then atoms of one element are different from the atoms of all other elements. I think do I have this right? I do. As far as circling different there. So compounds are composed of atoms of more than one element, and the ratio in which they combine are present is either an integer or a simple fraction. And then a chemical reaction involves the separation, combination, or rearrangement of atoms. So I think we talked about last time as far as hydrogen plus oxygen to make water. So that is a separation and then a rearrangement. Now, how that occurs is an energy interaction, and that energy interaction energy goes in over here to break bonds, and the energy is given off when bonds are formed. So as far as Dalton's atomic theory, the idea is looking at compounds that have been formed from what elements, and then you can see that chemistry is a lot like math that we talked about, is that it's kind of got like variables and that you can combine like terms. And this looks similar to the formation of water, but it doesn't show these things in its diatomic form. It shows them as their atomic form. So it is true that you would think about if this was diatomic, that these bonds would have to be broken in order to recombine into something different. And this would be a chemical change. So Dalton's atomic theory was based upon this idea that things are individual atoms that go to form compounds in certain ratios. And then this is a ratio of 2:1 for hydrogen to oxygen. So as far as the law of conservation of mass is concerned, this was evidence that when things combined, they combined in a certain way and that nothing was lost or gained as far as mass was concerned. And we'll also see that there's a law of conservation of energy, that energy is neither lost nor gained during these changes. So talking about our cathode ray tube, the cathode ray tube, again, we're looking at matter. We're looking at the subatomic particles. So the cathode ray tube helped to understand what atoms were made of, because as a voltage was put across here, you got this cathode ray. That cathode ray was unknown what it was, but it was known that when you put electricity and you put a magnetic field, it responded in a certain way. And what Thomson did is that he tweaked this electric field and the magnetic field such that this all was hit this spot. And then from doing that, he could figure out what the charge to mass ratio was of an electron. So the electron cathode rays was determined to be electrons, and those electrons, that's not a 5, that's an S. The electrons were determined to have a negative charge, and that negative charge, by tweaking the electric field of the positive and the negative, and then the magnetic field, it could be determined of what the actual charge to ratio was, mass to charge ratio. So this is another picture of a cathode ray tube, and that how it's responding to a magnetic field, not how it's responding to an electric field. Millikan came along and was looking at these results and said, well, how can I determine what the exact charge on that charged particle is in the cathode rays? So what he did was make this fine spray, and then it would fall at a certain rate that was determined by gravity. And then he could mess with this electric plates again, the positive and the negative. Those could be tweaked to a certain value of an electric field, and that electric field was measurable. And then if you could get that drop to just suspend, then he could determine the mass of the electron based upon the mass to charge ratio that Thomson determined. Now, what Millikan was doing was determining the charge, this Q. This Q is a charge that turns out to be, let me see if we can get here. Here it is, the charge. 1.6 times 10 to the minus 19th coulombs. Now, why do we care about this? This is a physicist world where they were really looking at what matter was made of. In chemistry, we're really going to focus on now what those 3 subatomic particles are. Now, of course, this using dimensional analysis, and if you have numbers like this, you can determine the mass of an electron, which could never have been measured on a balance, but it was measured through other means, through electricity and magnetism. So as far as chemistry is concerned, our real goal is just kind of, well, what are we doing here at this point? We want to know the subatomic particles and how they make up an atom. So let's go to the next slide, which is probably our more subatomic particles that we're trying to figure out. Up to this point, electron. Thomson and Millikan worked on figuring out the charge of the electron and the mass of the electron. So Thomson's model, now trying to figure out what an atom was consisted of. So this one, I think I showed you guys this last time. I don't know if it'll play for us here, but this was the plum pudding model. And that plum pudding model said that if electrons were distributed throughout like raisins in plum pudding, if alpha particles, which are positively charged nuclei, were sent through here, you would not see any change of those alpha particles' direction. So they would just go through, and then you would see kind of like a spot on your film up here that would show no deflection or no interaction. Let's see if we can play this. So there it goes. And so this was the prediction. This was the hypothesis for Thomson's model of the atom, that there would be no deflection. So Rutherford came along and said, well, if that's true, let me try another experiment. Let me try that experiment and make some sort of thin atoms, thin foil that had a distribution of gold atoms in there, and then shoot those alpha particles through, and those alpha particles were a positive charge. And what he found, though, is most of them went through an empty space, but every once in a while you had a deflection or you had a bouncing back. And so that meant that there was tiny positive charge concentrated in the center of the atom, and that proton has a positive charge, which is opposite of the electron. And that the mass of the proton, I do not believe this experiment determined the mass, did turn out to be this value here. So this is another one of those PhET animations that I was showing you. And that PhET animation is showing you the results of the Rutherford experiment, where that the alpha particles went through, and sometimes they were deflected, and then sometimes they actually bounced back. So I don't know if we see a bouncing back, but we do see a deflection here of those alpha particles, which help figure out what the atom was made of. So then the neutron, Chadwick, that was another one of our subatomic particles. We did electrons with Thomson, we did protons now with Rutherford, and now we're looking at the neutron, which is Chadwick's experiment. And his experiment, we watched a video last time, was showing alpha particles going through a beryllium sheet of metal. And because beryllium is a metal, and so you could make it into a sheet just like they did with gold. And that shooting those alpha particles in there caused neutrons to be given off. So carbon should have been left over. If you remember, there's like a picture down here of that experiment where those alpha particles came through, and they went through this wax. And that when they went through the wax down in there, they changed into protons, and those protons could be detected. So anyway, that's how Chadwick determined the existence of the neutron. And then that neutron, by looking at these numbers, you could see beryllium is number 4 here, and this guy is 4 too, is that there's mass interactions going on between these transformations between an element from one thing to another. And if that occurred and this beryllium was changed into carbon, there had to have been an exchange of mass, and that exchange of mass was this neutron. So I left you that link if you wanted to go look at that, to look at, understand that experiment again. So here's our 3 subatomic particles. Again, in chemistry, what do we care about? Electrons, protons, and neutrons. An exchange of electrons means things become ions. Protons and neutrons usually do not get exchanged. When we go to nuclear chemistry, they do get exchanged, like on our previous slide in Chadwick's experiment. And then you exchanged elements. One was beryllium got changed into carbon. So the relative charge on these things, positive for protons, negative for electrons, and 0 for neutrons, and the actual charge here in coulombs of an electron and a proton. And then the actual mass. So remember, in chemistry, what do we care about? We care about atoms, and atoms have masses. So if I have an atom, say of helium, and it has a mass number of 4 and an atomic number of 2, say it's neutral. If I were to say and add up the masses of that made up a helium nucleus, I would get the mass of one helium atom in grams, which of course is going to be really, really small. And in chapter 3, we learn how to scale that up using a mole and what a mole means. But if I still wanted to figure out the mass of a helium nucleus, I could, and by the subatomic particles, I could just add them all up, and it works. So the mass of the proton, the neutron, I was just giving you the size. I mean, electrons are teeny tiny comparatively. So as far as atomic number, mass number, and isotopes, atomic number is the number of protons, mass number is protons and neutrons. And then to look at isotopic notation, isotopes are atoms of the same element but with different numbers of neutrons. So as far as isotopic notation, you have your symbol, you have your mass number, you have your atomic number, and here's some examples. Uranium-235 means it has 92 protons because that's its atomic number, and this is neutrons plus protons. So you could just do a quick subtraction to get your number of neutrons here. Isotopes of hydrogen are protium, deuterium, and tritium, and there's your isotopic notation for those. As far as using this, you have your isotopic notation like carbon-14, and you can just do a subtraction to get your protons and your neutrons, and then if it's neutral, those are going to be equal. Same thing for carbon-11. As far as the modern periodic table is concerned, the periodic table is a listing of all the elements with their atomic number and their mass number. Now this picture is not showing the mass number, it's only showing the atomic numbers, but a period is the rows. A group and a family are the columns. And then we have special names for these. Alkaline metals, column 1, alkaline earth, column 2, halogens, column 7 or 17, noble gases, column 8 or 18. This chemistry in action was just a little fun thing just to see where are the elements in the Earth's crust. And in the Earth's crust, most of it is oxygen because of it being sand, and sand was silicon dioxide. We talked about the Earth's core, which was is understood to be made of iron. I'm not really sure how they know that. I don't have the experiment for that in my mind. The mantle and the crust, what we're talking about is the Earth's crust. Now I wonder how they know this. It must be taking, kind of drilling cores and then analyzing the core as far as you can go down, I guess. I don't know a lot about that geology-wise. Trace elements are in the human body. Well, I've zipped by that, but you guys can look at and read that chemistry in action about the distribution of the elements in the Earth and in the human body. But a molecule is an aggregate of 2 or more atoms in this definite arrangement. So here's a molecule of hydrogen, a molecule of water, molecule of ammonia has this shape because there's a pair of electrons here. This guy has this shape because he has a pair of electrons here. We'll talk about shapes kind of in chapter 10, so that's at the end of the course. And then here is a molecule of methane. Molecules are covalent compounds, and covalent compounds are made up of nonmetals. So a diatomic molecule contains only 2 atoms. These are all diatomic molecules. These specifically would be diatomic elements. So a polyatomic molecule contains more than 2. So these are all polyatomed, many atomed. So an ion, though, is a group of atoms that has a net positive or negative charge. Cations are positively charged, so it must lose 1 or more electrons to become a cation. Like sodium loses 1 electron to become sodium cation. So now it has more protons than it does electrons. An anion is the opposite of that. It's negative, and it must gain electrons. So to make sodium chloride, Sodium gives away its electron, so I'm going to put this little electron here. And then chlorine individually has 7 valence electrons, if you remember those from before, from your previous chemistry courses. So this guy pops into there, loses his electron, becomes positive, chloride becomes negative. Chloride becomes larger when that happens because there's less of an attraction here, and sodium becomes smaller because there's more of an attraction for the 10 electrons. You got one extra proton pulling in, but you have an extra electron that doesn't have a corresponding proton, so then it doesn't pull in as much. So it actually gets a little bit larger in its radius. So a monoatomic ion contains only one atom. So this is the sodium ion, the chloride ion, and the calcium ion, oxide. You'll notice all the negatives have an "ide" ending, whereas the positives do not. Polyatomic contains more than one atom. So these are polyatomic ions. Now we're showing these ions without their counter ion, but if I were to show a compound, say for example sodium nitrate, you would not see any charges, you would just see the elements that make it up. So as far as looking at these ions, we have to recall that when it's positively charged, that means it's lost electrons. So in this example, it had 13 protons because it's aluminum, but it only has 10 electrons because it must have lost those 3 to make 3 plus. So as far as what I call half reactions here, this is aluminum metal. I'm not sure why it's doing that little line there, but aluminum metal is oxidized to aluminum 3 plus. That's what's happening on the molecular level. And 3 electrons were lost. There's 3 of them were lost to somebody else. So there had to aluminum had to have undergone a chemical reaction for this to occur. This is the selenide anion, Se. So this is not an oxidation. This was oxidation is loss. This is reduction is gain. So I'm giving you some heads up on chapter 4. So selenium gains 2 electrons. And the reason it does that is because selenium is like oxygen, and it has 6 valence electrons. So you'll notice there's 2 holes right here. So those holes could be filled by electrons from somebody else. And when it does that, it becomes Se, but now it has 8 valence electrons, and it has a -2 charge. So that's called reduction. And now if I was looking for protons and electrons, it has 34 protons, but it must have 36 electrons. Okay. So as far as looking at some common ions, this is a table out of your text. So you want to make sure to know that everybody in column 1A forms a positive 1 charge preferentially, or even period. It doesn't form anything else, any of these elements. Same with these elements in column 2A. Column 3A, this guy forms a positive 3 charge. Can't make that determination of these other ones down here. And then these are the most common charges for some of these transition elements and these elements that lead and tin like to form +2 and +4. Then these nonmetals form negative charges, or anions, and those are their preferential charges. And that doesn't mean they don't form other charges, but what this table is showing you is ionic compounds. If an ionic compound forms between magnesium and oxygen, that's what it will do. However, if you get a covalent compound between nitrogen and oxygen, you might get different charge values, but they're not really charges as we see here. They are what we call formal charges, which is who's sharing more or less, but that kind of comes later. So in what you see here is showing the charge that will form between elements if they form a compound, an ionic compound. So as far as figuring out, just understanding how to write these things, a molecular formula has the number and type of atoms. So here again is hydrogen, water, ammonia, and methane. The structural formula shows how they're attached. Now you'll notice it does not show there's other electrons here on those guys. It doesn't show those. Ball and stick models are really, the goal is to show their shapes. Those electrons are there, but that's what the reason this has this shape. This is called bent or V shape, is because of those guys pushing. They have to have some space, so they push those down a little bit. That's called a ball and stick model, and then this is called a space filling model. And space filling model is just going to show what it really looks like. This is not what it really looks like up here because of your bond showing it like they're separated from each other, but they're not. They're snuggled in like that. And then again, you have your lone pairs kind of off of here, but we can't actually see the lone pairs. We just see the effect of them, which is the location of the other atoms with respect to the central atom, this being central here, this oxygen. As far as molecular and empirical, molecular actually says the number and gives the actual number and type of atoms. The empirical gives the lowest ratio. So the molecular and empirical for water is the same, but for glucose, you can reduce it. So a lot of times for an empirical formula, I do this type of thing, and that shows that if it's an empirical formula, to get to the molecular formula, I would have to multiply everything by 6. Empirical is experimentally determined, usually by percentages of elements in a compound. So then there'll be a percent carbon, a percent hydrogen, and a percent oxygen. So this is ozone, and its empirical would be O. And then here's N2N4, and if we can N2H4, and then if we can reduce that, we just get NH2. But again, I would put that to differentiate. Ionic compounds are cations and anions, and in this case, the formula is usually the same as the empirical formula because it's the lowest ratio anyway. So as far as the cation and anions go, each formula unit must equal 0. So here's an example of sodium chloride, and these crystals, we grow crystals like this in our lab for, I think, experiment 4. Experiment 4, we can grow some really neat sodium chloride crystals, and these like to put an X in there, and that's sometimes how you can tell them apart. It's hard to tell them apart from other ionic compounds. We also study KCl, which does the same type of crystal structure, and we also study NaNO3, which does the same type of crystal structure. They're all kind of cubic, but slightly different. So anyway, ionic compounds have these what's called formula units. You see an NaCl, Na being the gray, and then Cl being that reddish color. So as far as ionic compounds, we have metals and nonmetals, and this is just kind of this picture out of your book was showing the most reactive metals and the most reactive nonmetals. So you would see compounds forming between these, like lithium and oxygen. If you recall, lithium has 1 valence electron, everybody in this column does. And then if I put it together with oxygen, a single oxygen, it has 6 valence electrons. But you would see that you would need 2 lithiums in order to make this compound. So you would have a lithium there, one would go here, and your formula would be lithium, Li2O. So as far as figuring out the formulas, I was just giving you an example of that on the previous slide. Each one of these compounds are made up of the ions of the individual elements. So aluminum oxide is made up of 2 aluminum, 3 pluses, and 3 oxygen, 2 negatives. So as far as the aluminum 3 plus, there was 2 of them. So since there was 2 of them, that gives a positive 6, and then 3 of these gives a negative 6, and that's where your 0 comes in. Calcium bromide, same way. What I'm showing you is that it backs out each way to make sure that you have an overall 0 charge for each ionic compound. Now carbonate is held together as a grouping, so this whole thing is -2, so that's why I needed 2 of the sodiums. So as far as naming ionic compounds, often a metal and a nonmetal is an ionic compound. An anion has the "ide" ending, so this guy would be barium chloride. This one, potassium oxide, and this one, magnesium hydroxide. So this guy's +2, and this guy's -1, but there's 2 of them, so that's why it adds up to 0. And this guy is potassium nitrate, NO3 being nitrate. So if it's a transition metal, though, which are the metals in the middle of the periodic table, sometimes they can take more than 1 charge. And if you remember, lead and tin also took more than 1 charge. Lead and tin was right here. So we have to differentiate between the 2. So in this case, this is iron 2, and that would be iron 2 chloride. This would be iron 3 chloride. Now there's another way of naming these, the IC and the US system. And this guy would be called ferrous chloride. Now, how do I know that? The OUS ending is designated for the lower of the two charges, and the IC ending is designated for the higher of the two charges. So this would be called ferric chloride, and the iron 2 is ferrous. Now this guy is Cr2S3, so what is Cr? That's chromium. I can determine the charge of chromium by this value here, this 3. So this guy is chromium 3 sulfide. And there he is. So as far as the ic and the us, we would have to know the two charges that chromium forms. Is chromium 3 the high or the low of the two? So we should see some tables here coming up soon that will tell us that. So as far as this ide ending, this table out of your textbook is just showing you where the ide shows up. Carbide is the C4 negative. It's also used for this anion. I'm not sure why, but it was a traditional name. And this C22 negative is also called carbide. Nitride and phosphide. Anyway, here's all the ide endings on these individual monoatomic anions. So here is the table I was telling you about because I was thinking about chromium. Let's look for chromium. Chromium 3, remember we just named chromium 3 sulfide, and it has a 3 positive charge, and it's taking the ic ending. So that must mean that there's a lower of the two. So I would guess that there is a chromium 2 plus. Actually, there's a lot of them. There's chromium 6. There's all different ones, but traditionally chromium 3 is the chromic. I have to look up which one is the chromus. I think it's got to be the 2 plus, but I'll have to check it to make sure. So this table is out of your book. You can use this to put together and make compounds. Like if I put aluminum and chlorate together, you'll notice aluminum is positive 3 and chlorate is negative 1. So if I were to write a formula for this, it would be Al, and then it would be ClO3, and then there would be 3 of them, because each one of those is only negative 1. So as far as molecular, we're done with ionic for the moment, going on to molecular compounds. Molecular compounds consist of 2 nonmetals, or sometimes metalloids. There are some common names, of course, like water, ammonia, and methane. Element to the furthest in the left and closest to the bottom is placed first in the formula. So for example, H, except for H. I mean, well, H, where is hydrogen on the periodic table? He's to the left of oxygen, so he is placed first. Where's nitrogen? He is to the left. Where's carbon? He is to the left. If more than one compound can be formed, you have to use prefixes. So for example, HI is hydrogen iodide. There is no mono here, and there is no mono here. That is kind of a technicality for any hydrogen compounds. You don't use mono at all. And you don't use any prefixes, really, because H2S, you would think is maybe dihydrogen sulfide, and it's not. It's just hydrogen sulfide. That's the hydrogen rule. You know, I don't really see that anywhere listed, but it might be. I'll have to look more closely in your textbook. Let me know if you can find it in there, because it just kind of disappears and falls through the cracks because it's traditional naming system. This guy would be nitrogen trifluoride, sulfur dioxide, dinitrogen tetrachloride, nitrogen dioxide, and dinitrogen monoxide. So you can see the di shows up here and the mono over here. So as far as looking at and going through a flow chart of what kind of compound is it? Is it a metal or a non-metal? If you know, and in what form? So if you have a metal and a non-metal together, that's ionic. And then is it only one charge value, or can it have more than one charge value? That dictates how you name the compound. If it's molecular, you can use those prefixes, and that tells you how many of each are in your compound. So as far as the hydrogen rule was concerned, we saw that this would be named hydrogen oxide, and then if you name this guy, you would see him named hydrogen peroxide. And peroxide is a special oxide anion. Acids. Now acids, you kind of want to throw those in there at this point. Acids is a substance that yields hydrogen ions when dissolved in water. So HCl gas and HCl in water. This guy would name the HCl gas as hydrogen chloride, but once you put it in water, it becomes hydrochloric acid. So when it's pure substance, it's hydrogen chloride. When it's in water, it becomes hydrochloric acid. So when you write the behavior of an acid, you're saying, well, if it's an acid, it donates its hydrogen. And actually, the way the arrow should be pointing is that what it does, this lone pair goes over and picks up the hydrogen to make H3O plus, which is hydronium, and the counter ion. Now, as far as this hydrogen ions up here, it produces hydrogen ions. That's because hydrogen, this H plus, is a shorthand for H3O plus. So these binary acids are what we were just looking at there, like hydrochloric. There's the hydro plus the ic ending. So these are some common binary acids that you might be already familiar with. Hydrochloric is a very common one, but then we have things like hydrocyanic, even though that's not strictly binary, but it has a negative and a positive like that. And then hydrosulfuric acid comes from hydrogen sulfide. Oxoacids are acids that contain hydrogen, oxygen, and one other element, and that one other element is usually a nonmetal. I think it almost always is, or a metalloid. So when you name it, it's named with the ic. If it comes from the ate, like this came from nitrate, it becomes ic, and then you put acid on the end. This came from carbonate, so it becomes ic, and then put acid on the end. Comes from phosphate, phosphoric, comes from chlorate, chloric. So you see the pattern. If it ends in ite, it gets an us ending. So you get nitrous acid because it comes from nitrite. Phosphorus comes from ite. Chlorus comes from ite. Now, sometimes we have more than two. You see this is chlorite. We had chlorite and chlorate. So chlorite and chlorate were kind of the base ones, but then we even have more. This guy's called perchlorate. But since it's ate, it still becomes ic over here. And this is ite, so it still becomes us over here. But now you use the hypo and the per to differentiate. A base is something that yields hydroxide ions when dissolved in water. So when dissolved, this is a little bit of a misnomer because it's not dissolved. When sodium hydroxide dissolves in water, it actually reacts with water. It gets really, really hot. So that means that there's a reaction of the hydroxide with the water. And sure enough, a reaction of hydroxide, once it dissolves, you could say, and then there's a water molecule in here, it will react with water. So this guy would go pick off one of those. Now it looks like nothing happened, but something did happen. That one of the water molecules in the original solution was one of its hydrogens was ripped off. Now, sure enough, there's that hydroxide, which screams base to us, but it is a chemical reaction, and I can know that because a lot of heat is given off. So sodium hydroxide is a base. Calcium potassium hydroxide is a base. Barium so there's that there's a hydroxide in each one of those. Hydrates have a water molecule attached to them in their crystal structure. And these are named by saying how many water molecules are there. Barium chloride dihydrate. There's a monohydrate. There's a heptahydrate. And these are polyatomic anions here. So this is a sulfate. There's a nitrate. Tetra meaning 4, hepta meaning 7, and so on. So we can drive off the waters that are stuck in here by applying heat. And it becomes anhydrous. And when in our I think it's our second experiment of the semester, you will determine whether something is a hydrate by heating it and then watching for condensation of water on a glass. So as far as common names, we looked at this the other day on our PowerPoint in lecture, is that there's common names for lots of things, and I think this is incorrect. See, here it is, this dihydrogen monoxide. I'm still not sure, there's like some confusion of why that's labeled, because if this is dihydrogen monoxide, why isn't this dihydrogen sulfide? And so anyway, you'll see it labeled in both ways, but I think it's almost like a little bit of a confusion of what the real name is. So as far as the hydrogen rule is concerned, you should not be doing that. It should just be hydrogen oxide. Okay, so there's some common names, Epsom salts. These are all hydrates down here that have their common names. Washing soda and baking soda, all those are common names for these chemical compounds. So I think that might wrap it up for us. And then if you needed to hear this again, or if it would help, lecture videos module in D2L.